what we want to do is to go from the basics of Bayesian theory all the way to some of the latest ideas, and includes some of the latest applications of Bayesian inference, some of which are still being developed as we speak. I've put here, not for you to read now particularly, but some suggestions for further reading, but you'll have the PDFs of the lectures that you can refer to later. So some suggestions of further reading if you want to take this a bit further. So let me give you an outline of at least some of the topics that we will cover. This is not everything, but just to give you an idea. We'll start with a review of probability, and I'll spend a little bit of time on Bayes' theorem, and later I think we'll do the same to reinforce the ideas. Most of the time we will be talking about parameter inference, inferring parameters from data, and many of the projects that you'll be involved in fall into that category, and it's the thing which is we spend most of our time doing. One of the issues that we have to deal with in Bayesian analysis is the prior, and so I'll say quite a bit about the prior, and Nietzsche will also talk about the importance of the prior, how you sometimes have to be a little bit careful about it. There are some other concepts which are important, such as marginalization, posteriors. We'll say a little bit from a theoretical point of view on sampling. Much of what you're doing in the projects will be using various different samplers to sample the probability distributions, Monte Carlo, Markov chain, Hamiltonian Monte Carlo, and so on. In another category, there's the problem of model selection. So I'll come on to this in a moment, but essentially the sorts of problems that we deal with are either parameter inference problems where we assume a model. So we assume, let's say, lambda CDM, and we want to infer the values of the parameters of the model, which are omega matter, Hubble constant, and so on. But there's another class of problems which are, in a sense, a higher level question to ask, which is the model correct? Is lambda CDM correct? Or are we using the wrong model, and should we be using something which is based on brain worlds, for example? So we can address these questions statistically as well, and we can work out the probability, the relative probability of, say, lambda CDM versus a brain world model. And then we'll do some more advanced topics towards the end. So let me start by showing you some data that you've all seen before. So this is actually WMAP data, and this is some statistics of the WMAP data showing the correlation of the temperatures in pixels separated by a certain angle. So here is the cosine of the angle between the two pixels, and up here is the average value of the product of the temperature fluctuations at the two pixels. And so if you see that, if you look at this, then you see that we have three curves on here. If we ignore the blue one, but have a look only at the black one and the green one, then here we have data which is being confronted with theory. So the data from WMAP is the black line here. And lambda CDM, with the best fit parameters, is the green line here. So as you can see, lambda CDM is a very good fit to the data. We all know this, that lambda CDM fits the data extremely well, and it's very clear from this that that's the case. It's a beautiful fit to the WMAP data with the lambda CDM model. So why is this surprising? So this looks terrible, but we know that lambda CDM works. So how can we confront theory with data like this and claim that this is a good fit to the data? So in order to answer that question, we need to have a very good understanding of the statistical properties of the data. So there's another way to represent the data and to do the comparison, and this is the one that you normally see, which is to look at the power spectrum of the fluctuations. So this is the amplitude squared of the Fourier coefficients, effectively, or the spherical harmonic coefficients, as a function of multiple moments. So this is an expansion in spherical harmonics of the temperature field. And then you plot the power in the different modes as a function of angular scale. So there's large scales out here and small scales here. So here you see a very different story, or what seems to be a very different story, that the data and the theory, the best fit parameters, seem to work very well. So how do we reconcile these two now? How can these both be right? And the answer is in the statistical properties of the data that you choose to use. So here, essentially, these data points are almost uncorrelated. The noise moves them up and down in an essentially independent way, so that we can just quite reasonably look at the fit of the line through the points and say, yes, that seems to fit very well. There's maybe a few outliers, but basically that is a very good fit. So here, on the other hand, these data points, if you do a correlation function like this, the data points are highly correlated. They're not independent of each other, and you can move them all up and down together. So this curve is the Fourier transform, or spherical harmonic transform of this curve. So they basically have the same information in them. But if you change some of these long wavelength modes, so you just change this mode here, one or two of these modes here, then all of these points can move up and down together. So actually, the probability of getting a data set that looks like a black line, given that the expectation of the statistic in theory is the green line, the probability of getting the black line is actually not very low. It looks very bad, but it's not very low, because just by changing one or two modes, you can move things around a lot. So whatever statistics you end up using, in this case correlation functions, in this case the power spectrum, then you need to understand the statistical properties in order to be able to do scientific inference. Okay, now almost everything that we do in cosmology is an inverse problem. We want to go from data back to theory. So usually it's relatively straightforward if you have a theoretical model to predict what the data should look like. But that's not the problem that we're dealing with. We want to go backwards. We have a set of data, and we want to go backwards and say, what does that tell us about the theory? What does that tell us, for example, about the parameters of the theory? And that's generally harder. We need to do some work, and much of this course is giving you the tools to be able to do that, inference. So the sorts of problems that we could deal with, I mentioned this a little bit earlier, are hypothesis testing. So you might test some particular hypothesis. Within the framework of a model, you do parameter inference, and we have this higher level question of whether the model itself is correct. So examples of these types of problem are, say, hypothesis testing. Is the CMB radiation consistent with being a Gaussian random field? So we know theoretically from inflation that the field should be very, very close to being a Gaussian random field. So one could ask the question, are the data consistent with that hypothesis? Another one is parameter inference in a Big Bang model. What are the values of what's the value of the matter density parameter, say in that CDM? And model selection, is the Big Bang theory favored over other models such as the old steady state theory? The answer is yes. A more interesting question and more current is the gravity law general relativity, or is it a different theory? That's a much more difficult question to address, but it's one that you can address with the techniques which you'll hear about this week. Okay, so those are the sorts of questions that we are trying to address with cosmological analysis. How do we do it? Well, let me give you a review of probability, and in particular to discuss the differences between how Bayesians see probability and how frequentists see probability. So there are these two schools of thought of what probability means. To a frequentist, then the probability describes the relative frequency of outcomes in infinitely long trials. In other words, you do an experiment many, many times, and you count the number of times you get a particular outcome, and the probability is the ratio of those two in the long term, when you've taken many, many trials. The Bayesian view is quite different from that. It's that the probability basically quantifies our degree of belief, or state of knowledge, if you prefer. And here we have the idea that we have a logical proposition, which may be true or false. And the conditional probability, P of A given B, so this vertical line means given B, what is the probability of A? And what that means, if we look at it in slightly more detail, it's the degree to which the truth of some logical proposition B implies that the logical proposition A is also true. So, in other words, if B is true, then what is the probability that A is true? So we'll use this notation, P of A given B, to indicate that. So the Bayesian view seems to be what we want out of a cosmological experiment. So the sorts of questions we would like to ask are, given the Planck data, for example, then what is the probability that the density parameter of the universe is in a certain range? Okay, so what do we learn about the density parameter of the universe as we do an experiment? To a frequentist, this doesn't make any sense. So a Bayesian would say we can work out the probability of the density parameter given the data, and that would be some function. To a frequentist, even that concept doesn't make any sense. A frequentist would say, well, the density parameter is not a random variable, it's a parameter, it has a certain value. So saying that there's a probability distribution for it doesn't make sense to a frequentist. But to a Bayesian, regarding probability as a state of knowledge, our degree of belief, if you like, then it does make sense that we can define a probability distribution for the density parameter, given the experimental data that we've collected. Okay, we'll see in a minute how we can use the tools of probability to answer that question. But let me just give you a refresher, a reminder of the rules of probability, which will lead us to Bayes' theory. So if we have some random variable x, then then the probability of x plus the probability of not being x has to be 1. That's the sum rule. The notation for not being x, or x not being true, is that there are various different ones, and I think I may use more than one in these lectures. So x bar or twiddles x would refer to the state of x not being true. The product rule is that the joint probability, so p of x comma y indicates the joint probability of x and y. That is given by the probability of y times the probability of x given that y is true. So that product rule will be used extensively as well. And the next one, which is an important concept which we'll use in many different ways, is the idea of marginalization. That if we have two variables, x and y, then the probability of x is obtained by summing up all of the joint probabilities of x and y, provided that that this is an exhaustive list. In other words, that all of the values of y here are included. we'll deal mostly, actually not with discrete systems like this, where the values of y take on discrete values, but with continuous variables, in which case these sums become integrals, and the p of x and y here then becomes a probability density. But if we want to work out the probability of x, then we can marginalize over the probability of y. So this action of integrating over the over other variables is called marginalization. So one thing that is not controversial between Bayesians and frequentists is the following theorem, which is Bayes' theorem. So we know that the joint probability of x and y is the same as the joint probability of y and x. They're interchangeable. And so by using these rules, then we can simply, by writing down the probability of x given y and the probability of y given x, making them equal to each other, then we get to Bayes' theorem. P of y given x is p of x given y times p of y divided by p of x. So nobody argues with that. That is the debate between Bayesians and frequentists is to do with what probability means. It's not an argument about whether this equation is correct. Nobody would dispute it. What it allows you to do, the main benefit of Bayes' theorem, is to reverse the order of the conditional probabilities. So if you know what p of x given y is, then Bayes' theorem allows you to work out what p of y given x is. So that's its main use, and we'll be using it basically all the time. So why do we need to do that? Well, the reason we need to do that is that the probability of x given y is not the same as the probability of y given x. And many of the mistakes that are made in the real world come from not recognizing this very simple fact. For example, if we say x is the state of being male, and y is the state of having a beard, as shown here, then roughly, actually maybe in Mexico I have to change these probabilities. The probability of having a beard if you're male is about 0.1, before Paris. But the probability of being male, given that you have a beard, is pretty much 1. So these two things are not the same. Actually, that's not Julie behind the camera. That's to give her credit for having taken the photograph. That is not a highly bearded woman. Okay, simple example that just illustrates that you have to be careful about the ordering of these two things. So let me give you an example from outside of pathology, just to reinforce this idea. In a minute I'll give you an exercise to do just to check that you understand it. Suppose we have a medical test for an allergy that gives a positive result with a probability of 0.8 if you have the allergy. So if you have the allergy and you take the test, the probability of it being positive is 0.8. But it also has a false positive rate, that if you don't have the allergy and you take the test, then there is a small probability that it also gives a positive result. And that probability is 0.1, let's say. Then let's say that this allergy is something which 1% of the population has. So the probability of having the allergy in the population is 0.01. So you take the test. What's the probability that you have the allergy? So you look at these figures and you think, well, this looks like a reasonable test. It works most of the time, 80% success rate. If you don't have the allergy, then it gives you the wrong result, but only 10% of the time. It seems quite reasonable. So it's probably a decent test to tell you if you have the allergy. Let's work it out using Bayes' theorem. The first rule, and I strongly encourage you to follow this rule all the time, which is that whenever you're faced with a problem of probability, the first thing you should do is to write down the quantity that you want to calculate. So that's rule 1. In this case, it's what is the probability that you have the allergy, given that the test is positive. So the test comes back positive, what's the probability that you have the allergy? That's the quantity that you want. So mathematically, if we say A is the state of having the allergy, and T is that the test is positive, then the quantity that we want to calculate is the probability that you have the allergy, given the test is positive, so P of A given T. Okay. So that's rule 1. Write down what it is that you want to calculate. Once you've done that, then you can use the machinery of probability theory to help you. Rule 2 is that there are no other rules. That's the only one I can tell you. But remember it, because it's useful. So what do we know? We'll do the mathematics in a moment, but let's just write down mathematically the probabilities that we know from this. So we know that if you have the allergy, given that you have the allergy, then the probability that the test is positive is 0.8. We know that the probability that the test will be positive if you don't have the allergy is 0.1. And we know that the probability of having the allergy in the first place is 0.01. So those are the things that we know. This is the quantity that we need to calculate. We want to calculate, so let's do it. So those are the things we know. So you'll notice that the quantity that we want is P of A given T. What we know, amongst other things, is P of T given A. So that's something which we can use Bayes' theorem to help us with. So we use Bayes' theorem, just write it down. And then, so we know P of T given A, we know P of A. We have to think about what goes on the bottom. So P of T on the bottom, we can use the marginalization. But the probability of T is the joint probability of T and A plus the joint probability of T and not A. Doesn't typeset very well, I'm afraid, but it equals A. So these are the two. In the joint distribution of T and A, there's two possibilities for A, either you have it or you don't. But the probability of T is the sum of these two. Then we can use the product rule on these things on the bottom. So the probability of T, joint probability of T and A is the probability of T given A times the probability of A, and similarly for the other term. So now we're in a position where we've written the thing that we want in terms of things that we know. So everything is known, and there you can put in the numbers. And it turns out that the probability that you have the allergy, given that you've taken the test and it's turned out positive, is only 7.5%. So it's not a particularly effective test. When you look at the raw numbers, it looks as though it might be quite reasonable, but in fact, you take the test and it tells you you've got the allergy, and in fact, the probability that you have it is only 7.5%. Okay, so Bayes' theorem is very useful for turning these probabilities around. Let me give you, since I've been talking for a little while, an exercise to see if you've understood this. How many of you are aware of the O.J. Simpson trials? A little while ago, it's about 20 years ago. Yeah? So let me give you a sketch of the case. O.J. Simpson was an American football player, and in 1994 he was charged with the murder of his ex-wife Nicole Brown. Other potentially relevant information to the case was that he was known to have physically abused his ex-wife. The details of this case are not very nice, but as a statistics problem, it's an interesting one. And it also came up in the trial, and a statistical argument was presented which was entirely false. Okay? So we'll do it properly, and you can see what the conclusion is if you do it properly. So the defense lawyer made the following argument. He said that only 1 in 2,500 abusers is a murderer. So therefore, the information that Simpson was an abuser was not relevant. Okay? Not relevant. The number of abusers that murder their partners is tiny, so it's not relevant. And this was not challenged by the prosecution. And the result, not necessarily of this particular piece of information, was, as you know, that Simpson was acquitted. So you'll do this calculation properly in a minute. So one piece of information that we have there, which is not disputed, is that the probability that you're a murderer, n, given that you're an abuser, is only 0.0004. So let's analyse this carefully, do some work at the moment. What key piece of information has been conveniently ignored by the defence in this case? There's a relevant piece of information that's obtained in this particular case, which is not encompassed, it's not covered by the probability that the defence lawyer quoted. Anybody?
She is already murdered?
Exactly. There's a body involved, right? So that is, I think you'll agree, an important additional piece of information that might change the probabilities. Okay, so we need to calculate probabilities that are conditioned on the fact that there is a body involved. There's another piece of information that you're going to need to be able to do this calculation. It's quite similar to the one we've just done for the trials, the medical trials. There's another piece of information which you need, which is that the probability of being murdered in the USA is about 1 in 20,000. Okay, so that's an additional piece of information. So with all of that information, the fact that there is a body involved and you have this additional piece of information, what is the probability, on the basis of this evidence alone, the statistical argument, obviously there are other factors that were relevant in the case, but on the basis of this alone, can you compute the probability that Simpson was the murderer? Okay, have a go. Let's agree on some notation. So let's say N is that Simpson, the statement that Simpson was a murderer, A is that Simpson was an abuser, and B that there is a body. So have a go and see if you can write down. Start with rule 1. What is it that you want to write down, want to calculate, and I'll give you a few minutes to have a go at that.